August 25th, 1944. German engineering officer Hauptmann Friedrich Weber stood at the twisted remains of the Pont de Normandie, studying calculations that should have guaranteed American failure. His demolition teams had spent 3 days preparing the bridge, placing shaped charges at precise structural points determined by decades of German engineering excellence. The detonation had been perfect. Steel girders twisted like paper, concrete supports shattered into rubble. The entire span dropped cleanly into the Seine River below, creating a crater of twisted metal and pulverized concrete that stretched 200 feet across the water. Weber's engineering manual, the standard text used by Wehrmacht construction units since 1938, stated with mathematical certainty that bridge reconstruction required a minimum of 6 weeks, with specialized equipment and trained personnel. The Americans would need to establish temporary ferry operations, creating a logistics bottleneck that would slow their advance by weeks, perhaps months. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Every hour of delay gave German forces time to retreat, regroup, and establish new defensive positions along the next river line. He lit a cigarette and watched American engineers arrive at the riverbank, young men in muddy uniforms who looked more like construction workers than military professionals. Most appeared to be in their early 20s, carrying equipment that seemed improvised rather than standard issue. No surveying instruments, no precision measurement tools, none of the systematic preparation that German military engineering doctrine considered essential for bridge construction operations. They'll try some temporary pontoon structure, Weber thought, making notes in his leather-filled journal. Standard procedure for emergency river crossings. It might last a few days before current and traffic destroy it. Pontoon bridges were tactically useful but strategically limited. Maximum load capacity of 15 tons meant Sherman tanks would need to cross individually at reduced speeds. Supply convoys would face hours of delay waiting for clearance to proceed across unstable floating platforms. His assessment was clear and supported by 6 years of military engineering experience across Poland, France, North Africa, and the Eastern Front. American combat engineers lacked the technical sophistication and systematic training that made German military engineering the standard against which all others were measured. German engineering schools required 5 years of intensive study. Wehrmacht construction doctrine emphasized precision, calculation, and methodical execution. These American soldiers looked like they'd been drafted from civilian construction jobs and given 2 weeks of basic training. Weber's report to division headquarters that morning had been confident. Enemy engineers arriving at destroyed Seine crossing estimate minimum 42 days before permanent bridge. Operational. Recommend establishing defensive positions on eastern bank to exploit logistics delay. The mathematics were undeniable. Bridge construction was a science governed by immutable laws of physics, material strength, and structural engineering. American industrial capacity might produce vast quantities of equipment, but they couldn't manufacture the expertise and systematic methodology that required years of professional training. 300 yards downstream, Second Lieutenant James Mitchell from the 541st Engineer Combat Battalion stared at the destroyed bridge with eyes that had learned to read structural failures like a carpenter reading wood grain. 26 years old, a civil engineering graduate from Virginia Tech who'd spent 2 years building highway bridges in the Appalachian Mountains before the Army drafted him in 1942. His hands were calloused from handling timber and steel, his coveralls stained with grease and mud from 3 months of continuous operations since Normandy. Mitchell had built 17 bridges in the mountains of Virginia and West Virginia, working for a construction company that specialized in rural highway projects where budgets were tight and deadlines were unforgiving. He'd learned techniques that engineering professors never taught in university classrooms. How to estimate load capacity by visual inspection rather than mathematical calculation. How to sink foundation posts through rock and clay without geological surveys. how to compensate for imprecise measurements through structural redundancy rather than careful planning. His company commander, Captain Robert Hayes, stood beside him with maps that showed 17 more destroyed crossings between their current position and the German border. Every major river, every significant stream, every culvert large enough to matter, the Germans had demolished them all during their retreat, following doctrine that assumed systematic destruction would slow Allied pursuit for months. The red marks on Hayes's map created a barrier of absent infrastructure, stretching across France like a defensive line built from mathematical certainty rather than concrete fortifications. "Lieutenant, division needs traffic moving across this river in 72 hours, Hayes announced, his voice carrying the flat certainty of an officer delivering orders that couldn't be questioned regardless of feasibility. Not pontoons. A permanent bridge capable of handling Sherman tanks and supply convoys 24 hours daily. General Patton's Third Army is running on fumes. Every day of delay gives the Germans time to establish winter defensive positions." Mitchell studied the demolished span, calculating load requirements and material specifications with the practiced efficiency of someone who'd built structures under deadline pressure that made military operations seem leisurely. The destroyed bridge had been an elegant arch design, probably constructed in the 1920s during France's post-war reconstruction period. Beautiful engineering, sophisticated structural calculations, built to last a century, completely irrelevant to current tactical requirements. He needed a bridge that would last 6 months, maybe a year. Long enough for Allied armies to reach Germany and end the war. Aesthetic elegance didn't matter. Architectural sophistication was irrelevant. The only requirements were load capacity and construction speed. Sherman tanks weighed 32 tons fully loaded. Supply trucks averaged 6 tons. If the bridge could handle 40 tons with safety margins and be completed before German forces established defensive positions at the next river crossing, it served its purpose. "Sir, we can do it in 48 hours, Mitchell replied, the words emerging with confidence born from experience rather than bravado. He'd built mountain bridges in worse conditions with less equipment. The difference was that in Virginia, nobody was shooting at him, and construction delays meant contract penalties rather than strategic defeat. Hayes studied the young lieutenant with the calculating expression of an officer who'd learned that promising the impossible and delivering the adequate often produced better results than promising the adequate and delivering nothing. 48 hours. I'll hold you to that, Lieutenant. Division is watching this crossing. If we prove American engineers can replace destroyed bridges faster than Germans can demolish them, it changes the entire tactical equation for the advance into Germany. The meeting at battalion headquarters that evening erupted in professional disagreement that barely remained within military protocol boundaries. Engineering officers who'd spent careers studying proper construction methodology stared at specifications that violated every principle of systematic bridge building that had governed military engineering since Roman legions, built spans across European rivers 2,000 years earlier. "You're proposing we skip foundation surveys?" Major Thomas Crawford, the battalion engineering officer, pointed at Mitchell's hastily drawn schematics with the kind of professional horror typically reserved for discovering structural calculations that predicted imminent collapse. No soil analysis, no load testing, no structural calculations. Lieutenant, bridges built without proper engineering methodology don't just fail, they kill people. This isn't some temporary structure we can abandon if problems develop. You're talking about a permanent span carrying military traffic continuously for months. Crawford had spent 23 years in the Army Corps of Engineers, building dams, levees, and military installations across the continental United States. He'd supervised construction projects that took years to complete, following systematic procedures that ensured safety and longevity. The idea of building a bridge, without geological surveys, without structural calculations, without the methodical verification that separated professional engineering from amateur construction, violated everything he'd learned during 2 decades of military service. Mitchell understood Crawford's concern but recognized it came from peacetime, thinking that had no place in combat operations. "Sir, German demolition teams destroyed this bridge, assuming we'd follow standard procedures. If we do that, they're right. The advance stops here for 6 weeks while we conduct surveys and calculate optimal structural designs. By then, Wehrmacht forces will have established defensive positions we'll be fighting through all winter." The argument represented fundamental disagreement about engineering philosophy that extended beyond tactical considerations to different worldviews about how problems should be solved. German and traditional American military engineering emphasized precision, calculation, and optimal resource utilization. Every component should be sized exactly for its load requirements. Every support should be positioned at calculated intervals. Every structural element should serve a specific purpose in the overall design. Mitchell was proposing something different. Build bridges using standardized components that could be assembled without detailed planning. Prefabricated steel sections, pre-cut timber supports, and foundation systems that relied on volume rather than precision. Instead of calculating minimum requirements and building to exact specifications, overbuild everything by 50% and accept that material waste was cheaper than time delay. The load capacity won't meet regulation standards, Crawford argued, his voice carrying the weight of professional authority earned through decades of systematic engineering practice. "You're talking about bridges that might collapse under heavy traffic. When a Sherman tank goes through your bridge deck into a river, the CART-ME investigation will trace back to the officer who approved construction without proper structural calculations." Mitchell pulled out his notebook, the same battered composition book he'd carried through 3 months of combat engineering operations. Pages filled with sketches, measurements, and observations from 17 bridges built since Normandy. "Sir, I've been tracking our bridge construction statistics since June. Standard methodology averages 42 days from initial survey to completed span. My company has built 5 bridges using modified procedures. Average completion time, 68 hours. 0 structural failures. Load capacity exceeding design requirements by 40 to 60%. The room fell silent as officers studied Mitchell's documentation. The data was undeniable. 5 bridges built in less than 3 days each, all supporting traffic that included Sherman tanks, tank destroyers, and heavy supply convoys. No collapses, no structural failures, no safety. Incidents beyond minor injuries typical of any construction operation. Captain Hayes spoke into the silence with the decisive authority of an officer who'd learned that wars weren't won by following peacetime regulations. "Major Crawford, I respect your expertise and your concerns about proper engineering methodology, but Lieutenant Mitchell has demonstrated results that meet tactical requirements. We're not building monuments, we're building tools to win a war. Different objectives require different methods." Crawford's expression showed professional resignation rather than agreement. He'd spent a career building structures designed to last decades through careful planning and systematic execution. The idea of accepting bridges that might only last months offended his engineering sensibility. But he'd also spent enough time in combat operations to recognize that tactical necessity sometimes overruled professional standards. "Lieutenant Mitchell, you'll have your 72 hours, Crawford announced, his voice carrying the formal precision of an officer documenting decisions for future investigation. "But I'm assigning 2 engineering officers to observe your construction methodology and document every deviation from standard procedures. When your bridge is completed, it will undergo full load testing before any traffic is permitted. If structural analysis reveals inadequate safety margins, construction will halt immediately regardless of tactical considerations." Mitchell accepted the compromise with professional grace. Observation and testing would slow operations slightly but wouldn't prevent completion. His construction methods might offend engineering professors, but the mathematics were sound. Overbuilding compensated for imprecision. Redundancy provided safety margins that careful calculation couldn't improve. The bridges might be ugly and wasteful, but they'd carry Sherman tanks across French rivers while German forces were still retreating toward the next defensive position. The real innovation wasn't technical methodology, but philosophical approach to problem solving. German engineering sought elegance through precise calculation of minimum requirements. American engineering would achieve reliability through excessive material application. Instead of building one perfect bridge that required 6 weeks of careful construction, build an adequate bridge in 2 days and accept that material costs were cheaper than time delays. Mitchell's team began work at dawn on August 26th with equipment that made traditional engineers uncomfortable. No surveying instruments, no soil testing apparatus, no structural calculation tables. Just prefabricated steel I-beams manufactured in Pennsylvania foundries and shipped to France by the thousands, timber supports cut from French forests, and pile drivers that could sink foundation posts through river mud without waiting for geological analysis. The first innovation was abandoning precision in favor of overwhelming structural redundancy. Where engineering manuals called for calculating exact load distributions and minimal material usage, Mitchell simply doubled everything. Twice as many support beams as calculations indicated necessary. Foundation posts sunk twice as deep as specifications required. Connection bolts installed at half the regulation spacing. German engineering achieved elegance through precise calculation that minimized material waste while maintaining adequate safety margins. American engineering achieved reliability through excessive material application that guaranteed structural integrity regardless of load variations or construction imprecision. The difference reflected fundamental philosophical approaches to problem solving that extended beyond bridge construction to how industrial societies organized production and resource allocation. His crew chief, Sergeant First Class Anthony Romano, had spent 15 years as a construction foreman in Chicago before the Army drafted him in 1943. Romano understood that military ranks meant less than practical experience when actual construction work began. He studied Mitchell's plan with the critical eye of someone who'd built structures where contractor profits depended on completion speed rather than engineering sophistication. "Lieutenant, we're going to waste about 30% more material than standard methodology requires," Romano observed, his Chicago accent softening technical criticism with practical acceptance. "But if it gets us finished in 2 days instead of 6 weeks, I'd say that's a pretty good trade. Let me get the pile driver crews positioned, and we'll start sinking foundation posts within the hour." The pile driver operations began with mechanical efficiency that would have impressed factory supervisors more than military engineers. No surveying to determine optimal post positions. No geological testing to identify ideal foundation depths. Romano simply marked positions at 10-foot intervals across the entire river width, creating a grid pattern that provided support density far exceeding calculated requirements. "If the Germans calculated we need one support post every 20 feet, we're going to put them every 10 feet, Romano explained to his crew. "If engineering manuals say sink posts 12 feet into river mud, we're going 16 feet. Everything gets doubled. It's inefficient as hell from a materials perspective, but it guarantees we don't have structural failures that stop traffic flow." The pile drivers operated with rhythmic precision that created a percussive soundtrack across the river valley. Diesel engines driving massive hammers that pounded timber posts through water and mud into bedrock below. Each post sank with steady progress measured in minutes rather than hours, eliminating the careful foundation work that traditional bridge construction required days to complete properly. Weber watched through field glasses from German positions on the far riverbank, his initial assessment evolving from confidence to concern as American engineering operations proceeded at speeds that violated every timeline his training indicated possible. The equipment being assembled looked too substantial for temporary pontoon structures. The foundation work involved pile drivers, sinking support posts at depths that exceeded requirements for anything except permanent bridge construction. By noon on the first day, Mitchell's team had completed foundation work that German methodology indicated should require 3 days of systematic preparation. The pile drivers had sunk 240 timber posts across the river bottom, creating a forest of vertical supports that stretched from bank to bank. No precise positioning, no careful measurement, just overwhelming density that guaranteed adequate support, regardless of load distribution calculations. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Sections arrived by truck convoy from supply depots that had been stockpiling bridge materials since the Normandy invasion. American industrial capacity had anticipated the bridge reconstruction problem months before combat engineers encountered it in the field. Factories in Pittsburgh, Gary, and Birmingham had manufactured standardized components by the tens of thousands. I-beams cut to identical lengths, connection plates pre-drilled for standard bolt patterns, timber decking milled to uniform dimensions that required no field modification. This was the innovation that German engineering officers couldn't replicate, even when they understood American methodology. Wehrmacht logistics operated on principles of efficiency and optimal resource allocation. Components were manufactured to specifications for individual projects. Custom fabrication allowed precise engineering but required extensive planning and calculation before construction could begin. American industry had taken a different approach, one that reflected mass production philosophy developed in Detroit automobile factories and applied to military engineering. Instead of custom components for each bridge, manufacture hundreds of thousands of identical parts that could be assembled in any configuration. Sacrifice individual optimization for systematic flexibility. Accept material waste in exchange for construction speed. Mitchell's engineers assembled bridges the way factory workers assembled automobiles on production lines. No custom fabrication, no individual measurement, just standardized parts fitted together in predetermined sequences that required minimal training and no engineering expertise. A crew that had never built a bridge before could follow assembly procedures and produce functional structures within days. The steel I-beams measured 30 feet in length and weighed 800 pounds each. Standard cranes lifted them into position across the foundation posts, creating a grid pattern of steel that would support the bridge deck. Connection crews followed immediately behind, bolting beams together using pre-drilled holes that aligned automatically when components were positioned correctly. Romano supervised the steel assembly with the efficiency of a factory foreman managing production quotas rather than a construction supervisor building unique structures. Beam number 1 goes on posts 1 through 4. Beam number 2 on posts 5 through 8. Keep the spacing consistent and the bolts tight. We're not building artwork here. We're building a road that happens to cross water. The observation teams from battalion headquarters watched with professional fascination as American engineering methodology abandoned precision in favor of systematic redundancy. Major Crawford made detailed notes about construction procedures that violated every engineering manual while producing results that appeared structurally sound despite methodological chaos. By sunset, on August 26th, steel superstructure stretched across the entire river width. The structure rising from the Seine looked nothing like the elegant arch bridge the Germans had demolished. Instead, it resembled a massive industrial platform, supported by hundreds of posts and topped with steel I-beams laid parallel like railroad tracks. Ugly, inelegant, wasteful of materials, but undeniably substantial. Weber's engineering assessment grew increasingly concerned as he watched American progress through the failing light. His field glasses revealed construction details that challenged fundamental assumptions about bridge-building methodology. The Americans weren't just working fast. They were using construction techniques that eliminated entire phases of systematic engineering that Wehrmacht doctrine considered essential. No foundation analysis meant they couldn't optimize post-placement for soil conditions. No structural calculations meant they couldn't minimize material usage while maintaining safety margins. No precision measurement meant they couldn't achieve the elegant efficiency that German engineering schools taught as the hallmark of professional construction. Yet somehow, the bridge taking shape across the Seine River appeared more substantial than temporary pontoon structures, while being assembled at speeds that should only be possible for emergency crossings. The contradiction challenged everything Weber had learned during 20 years as a military engineering officer. His report to division headquarters that evening contained calculations that contradicted his morning assessment. American engineers completing permanent bridge construction at rates that violate established doctrine. Estimate operational capability within 72 hours rather than projected 42 days. Construction methodology emphasizes material redundancy over structural optimization. Results appear tactically effective, despite violating engineering principles. The response from division came within hours, reflecting growing Wehrmacht concern about American logistics capabilities that exceeded German planning assumptions. Confirm American bridge construction timeline and methodology. Strategic planning depends on accurate assessment of enemy engineering capacity. If Americans can replace destroyed bridges within days rather than weeks, defensive demolition doctrine requires complete revision. The morning of August 27th brought renewed construction activity that confirmed Weber's worst fears. The Americans weren't just building one bridge quickly, they were establishing systematic procedures that could be replicated across every destroyed crossing in France. Mitchell's methodology wasn't improvisation. It was doctrine emerging from tactical necessity and refined through practical application. The decking crews began installing wooden roadway surfaces while steel assembly was still ongoing in other sections. Traditional bridge construction followed sequential phases where each stage needed completion before the next began. Foundation work finished, then structural steel installed, then decking applied, then finishing work completed. The process ensured quality through systematic verification at each stage. Mitchell ran simultaneous operations across the entire bridge length. Foundation teams worked at the far bank while steel assembly crews secured I-beams at the near bank. Decking crews installed wooden roadway surfaces on completed sections while welding teams were still connecting steel in other areas. The bridge grew from both ends simultaneously, meeting in the middle with connection work that required only minor adjustment rather than precise calculation. The organizational innovation reflected American industrial philosophy applied to military construction. Henry Ford had revolutionized automobile manufacturing by breaking production into parallel operations performed by specialized teams. Mitchell applied the same principle to bridge building. Instead of craftsmen who understood entire construction process from foundation to finishing, create specialized crews that performed single tasks repeatedly with maximum efficiency. Romano's decking crews consisted of soldiers who'd been carpenters, mill workers, and lumberyard employees in civilian life. They understood wood better than engineering theory. Their job was simple: install pre-cut timber planks across steel I-beams at maximum speed without worrying about overall structural design. The timber arrived pre-cut to standard lengths that fit between beams with minimal trimming. Pre-drilled holes aligned with bolt positions, assembly required hand tools and physical strength, not engineering expertise. Each plank gets 4 bolts, 1 at each corner. Romano instructed crews who'd been performing the same operation for 3 months across France. Tight enough to eliminate movement, not so tight you crack the wood. We're laying 1,000 planks today. That's 1 plank every 43 seconds if we work continuously. Let's move. The pace would have been impossible if each plank required custom fitting and individual calculation. Standardization eliminated complexity. Every plank identical, every bolt hole pre-positioned, every connection procedure rehearsed through repetition. Construction became mechanical execution rather than creative problem-solving. By noon on the second day, timber decking covered 2/3 of the bridge length. The roadway surface stretched across the Seine River like a wooden highway suspended on industrial scaffolding. Approach ramps on both banks allowed vehicles to access the bridge deck. The structure was operational in everything except official designation. Major Crawford stood at the near bank, watching supply trucks queue for bridge testing that military regulations required before traffic could be authorized. His professional assessment struggled with contradiction between methodology and results. Mitchell's construction violated every engineering principle Crawford had spent 23 years learning and applying, yet the bridge appeared structurally sound, possibly overbuilt given the density of support posts and redundancy of steel beams. "Lieutenant, I'm authorizing preliminary load testing," Crawford announced with the formal precision of an officer documenting decisions that might later be investigated. "We'll start with unloaded trucks, then progress to loaded vehicles, and finally attempt tank crossing if initial tests prove satisfactory. Standard protocol requires 72 hours of observation before authorizing unlimited traffic, but tactical considerations may override normal procedures if structural integrity appears adequate." The first test vehicle, a GMC 2.5-ton truck without cargo, rolled onto the bridge at walking speed. The timber deck creaked under load but showed no signs of structural distress. The driver accelerated to 15 miles per hour, normal convoy speed, and crossed the entire span without incident. The bridge groaned and flexed slightly under traffic, but remained solid. Second test. Loaded supply truck carrying 6 tons of ammunition and rations. Same results. The bridge handled the weight with structural deflection that remained within acceptable tolerances, despite lack of precise engineering calculations. The timber deck absorbed shock and distributed load across multiple support beams, exactly as Mitchell had predicted, based on experience rather than mathematical analysis. Third test. Sherman tank, 32 tons of armor and weaponry. This was the critical evaluation. If Mitchell's bridge could handle main battle tanks, it served every tactical requirement regardless of engineering methodology. The tank commander approached cautiously, aware that bridge failures with heavy vehicles typically resulted in crew deaths rather than minor injuries. The Sherman rolled onto timber decking with mechanical certainty that tested structural integrity without compromise. The bridge groaned louder under tank weight. Support posts flexed visibly as load distributed through foundation system. But nothing failed, nothing cracked. The structure held firm through the kind of stress testing that revealed whether engineering methodology or material redundancy determined ultimate load capacity. Weber watched American engineers guide the Sherman tank across the completed span on the afternoon of August 27th, exactly 48 hours after construction began. His field glasses captured details that would appear in intelligence reports read by Wehrmacht High Command, with growing alarm about American engineering capabilities that exceeded every German assessment. A permanent bridge, constructed in 2 days, using methodology that violated systematic engineering principles, yet capable of supporting main battle tank traffic continuously. The tactical implications were devastating for German defensive strategy that assumed destroyed bridges, provided barriers lasting weeks rather than days. His final report to headquarters contained conclusions that contradicted everything he'd learned during 20 years as a military engineering officer. American combat engineers have constructed permanent bridge in 48 hours using methodology that abandons established engineering principles in favor of material redundancy and standardized components. Bridge capacity confirmed through load testing with Sherman tank. Construction timeline and methodology indicate Americans can replace destroyed infrastructure faster than Wehrmacht forces can retreat to next defensive position. The response from division headquarters reflected strategic and desperation that would characterize German defensive operations for the remainder of the war. All engineering units increase demolition thoroughness, destroy bridges beyond repair using maximum explosives. Remove bridge approaches to complicate American reconstruction. Defensive doctrine assumes destroyed crossings provide barriers measured in weeks. American engineering capacity has reduced barriers to days. Adjust tactics accordingly. But the adjustment was impossible. German forces retreating across France couldn't spare time or resources for thorough demolition that might delay American engineers by additional days. Wehrmacht units needed to withdraw faster than pursuing Allied armies advanced. Every hour spent destroying bridges was an hour that allowed American forces to close distance and engage in combat that German commanders desperately wanted to avoid. The Seine River crossing established template that would be repeated across France, Belgium, and into Germany itself. Mitchell's methodology spread through American engineering battalions as officers recognized that speed mattered more than elegance in combat operations. By September 1, 1944, 17 engineering units were building bridges using standardized components and structural redundancy rather than precise calculation and optimal material usage. The statistics began accumulating in after-action reports that documented performance exceeding every peacetime engineering standard while violating every construction regulation. The 541st Engineer Combat Battalion alone built 17 bridges in September. Average construction time, 63 hours. 0 structural failures. Load capacity exceeding design requirements by margins ranging from 40 to 70%, depending on river width and foundation conditions. Other engineering battalions reported similar results. The 291st built 12 bridges in September. The 82nd Airborne Division's engineering companies built 6 bridges in 3 weeks. Across the European theatre, American combat engineers were proving that industrial mass production philosophy, applied to military construction, could achieve tactical results that systematic German engineering methodology couldn't match. Captain Wilhelm Hessler, a German intelligence officer assigned to analyze American engineering capabilities, compiled reports throughout September that documented bridge construction rates he initially dismissed as exaggerated Allied propaganda. The numbers seemed impossible. 23 bridges completed in the first week of September across 3rd Army's sector alone, 37 more in the second week. By month's end, American engineers had built 86 permanent spans across rivers and streams throughout liberated France. Hessler's analysis struggled with mathematical contradiction. German demolition teams required 3 days to properly destroy a bridge using shaped charges and systematic preparation. American combat engineers required 2 days to build replacement bridges using prefabricated components and standardized assembly procedures. The strategic calculus of defensive demolition had been completely inverted by American industrial capacity. His October intelligence summary contained a paragraph that would be quoted in post-war engineering studies for decades. American bridge construction has rendered defensive demolition tactically ineffective. Enemy engineering units replace destroyed spans faster than our forces can retreat to next river line. Standard defensive doctrine assumes destroyed bridges provide barriers delaying pursuit for weeks. American methodology reduces delay to days, eliminating primary tactical advantage of defensive demolition operations. The operational impact became clear when German forces attempted to establish winter defensive positions along river lines that had been considered naturally defensible terrain since medieval warfare. The Moselle River Valley, historically a barrier requiring weeks for armies to cross, was bridged by American engineers in 5 days using 17 separate spans constructed simultaneously by multiple engineering battalions. Wehrmacht defensive planning documents captured after the war revealed the extent to which American bridge-building capacity influenced German strategy throughout the autumn campaign. Staff officers calculated defensive positions based on assumptions about Allied logistics limitations that proved completely inaccurate when confronted with engineering capabilities that exceeded German assessments by factors approaching 10 to 1. Major General Walton Walker, commanding the 20th Corps during the advance across France, submitted a commendation report in October that captured strategic significance of American bridge-building capacity. Combat engineers have transformed river barriers from operational obstacles into minor tactical delays. German defensive strategy continues to emphasize demolition of crossings under assumption that bridge reconstruction requires extended timeframes. American engineering doctrine has rendered this assumption obsolete through systematic application of industrial production methodology to military construction. Mitchell received promotion to captain in October with assignment as battalion engineering officer, replacing Major Crawford, who'd initially opposed his construction methodology. The irony wasn't lost on anyone in the 541st Engineer Combat Battalion. The officer who'd argued for systematic engineering procedures had been replaced by the lieutenant who'd proven that wartime demanded different priorities than peacetime construction. Crawford accepted reassignment with professional grace that acknowledged tactical results outweighed methodological concerns. His final report to Corps Engineering Headquarters contained assessment that would influence American military doctrine for generations. Lieutenant Mitchell's construction methodology violates established engineering principles while achieving superior tactical results. Recommend formal adoption of standardized component bridge construction as official doctrine for combat operations. Peacetime engineering standards emphasizing efficiency and elegance remain appropriate for permanent infrastructure. Combat engineering requires different priorities where speed and reliability outweigh material optimization. The technique evolved through practical experience and accumulated innovations from dozens of engineering battalions operating across the European theatre. The November Construction Manual, issued by Army Corps of Engineers Headquarters, incorporated lessons learned from 6 months of combat bridge building, formalizing methodology that had emerged from tactical necessity rather than systematic doctrine. Standardized bridge components became foundation of American military engineering logistics. Steel I-beams manufactured in Pittsburgh foundries arrived in Europe by the hundreds of thousands, cut to uniform lengths that required no field modification. Timber supports were processed in sawmills established in the Vosges Mountains, providing construction material that eliminated dependence on supply lines stretching back to American industrial centers thousands of miles distant. The prefabrication extended beyond raw materials to include entire bridge sections that could be assembled on shore and positioned using crane equipment. Bailey Bridge components, developed by British engineers and manufactured under license in American factories, provided standardized structural elements that could be configured for different span lengths and load requirements without custom fabrication. British military engineers had pioneered modular bridge construction with the Bailey Bridge design in 1941. American industrial capacity took the concept and scaled it to levels that transformed tactical innovation into strategic weapon. By December 1944, American factories were producing Bailey Bridge components at rates exceeding 2,000 tons monthly, enough material to construct 50 permanent bridges every 30 days. The systematic integration of British design innovation with American mass production capacity created engineering capability that exceeded anything German forces could counter through defensive tactics. Wehrmacht commanders could destroy bridges, but American engineers replaced them faster than German units could retreat. The mathematics of warfare had fundamentally shifted from combat effectiveness to logistics capacity. By December, American combat engineers had perfected assembly procedures that reduced construction time even further. The Rhine River crossing at Remagen in March 1945 demonstrated culmination of bridge-building methodology that had evolved from Mitchell's original 48-hour Seine crossing. Engineers completed emergency bridge construction adjacent to the captured Ludendorff Bridge in 36 hours. Creating capacity for armoured divisions to cross into Germany despite German demolition attempts. The Remagen operation revealed how completely American engineering doctrine had evolved during 9 months of continuous combat operations. Mitchell, now commanding the 541st Engineer Combat Battalion as a major, supervised construction of 3 separate bridges across the Rhine within 72 hours. Total combined capacity exceeded that of the partially damaged Ludendorff Bridge that had been captured intact through tactical luck. General Dwight Eisenhower personally visited Remagen on March 9th to observe engineering operations that were enabling the largest river crossing in modern military history. He stood beside Mitchell watching Sherman tanks roll across timber decking suspended on steel I-beams, supported by foundation posts sunk through Rhine riverbed mud into bedrock below. Major, how many bridges has your battalion built since Normandy? Eisenhower asked with the informal directness that made him popular among combat officers, who appreciated commanders treating tactical success as more important than military protocol. 43 permanent spans and probably 60 temporary crossings, sir, Mitchell replied, consulting the worn notebook he'd carried since France. Total bridge length about 18 miles if you laid them end to end. Average construction time has dropped from 48 hours in August to about 36 hours now. The crews have gotten very efficient at standardized assembly. Eisenhower studied the Rhine Bridge with professional appreciation for engineering achievement that enabled strategic success. The Germans thought they could slow us down by destroying infrastructure. They didn't account for American industrial capacity applied to military construction. Your bridges have kept armies moving when traditional logistics doctrine said we should have stopped months ago. The statistical achievement documented in post-war engineering reports revealed scale of American bridge-building operations across the European theatre. 314 major bridges constructed between June 1944 and May 1945. Total bridge length exceeding 250 miles, if laid end-to-end. Average construction time per bridge dropping from 72 hours in August 1944 to 48 hours by March 1945, as engineering battalions refined procedures through continued practical application. German post-war analysis compiled by Allied intelligence teams revealed extent to which American bridge-building capacity had influenced Wehrmacht defensive strategy throughout the campaign. Staff officers interviewed after surrender consistently cited Allied engineering capabilities as decisive factor that rendered traditional defensive tactics ineffective against American operational tempo. Oberst Hans Speidel, Chief of Staff to Field Marshal Erwin Rommel during the Normandy campaign, provided testimony during interrogations that captured German military assessment of American engineering operations. We calculated defensive positions based on assumptions about Allied logistics limitations that proved completely inaccurate. American engineers replaced destroyed infrastructure faster than our forces could retreat and establish new defensive lines. Traditional advantages of defensive warfare were neutralized by enemy capacity to sustain offensive operations regardless of terrain obstacles. The strategic implications extended beyond immediate tactical advantages to reshape fundamental assumptions about military engineering doctrine that had governed warfare since Industrial Revolution. German military theory emphasized precision engineering and optimal resource utilization, reflecting industrial philosophy that assumed material scarcity required careful planning and measured construction. American methodology demonstrated that abundant industrial capacity allowed different approaches to military engineering. Instead of building bridges designed to last decades through careful calculation and precise construction, American engineers built bridges that only needed to last until Germany surrendered. The difference in perspective reflected broader philosophical differences between societies organized around different economic principles. Mitchell's post-war career included professorship at Virginia Tech, where he taught civil engineering students about relationship between construction methodology and strategic objectives. His course on wartime engineering became required curriculum for Army Corps of Engineers officers, attending advanced training, ensuring that lessons learned in France would influence American military doctrine for generations. The bridges themselves began disappearing in the 1950s as European reconstruction replaced temporary wartime spans with permanent infrastructure designed for peacetime traffic loads and century-long operational lifetimes. French, Belgian, and German governments rebuilt crossings using modern engineering that emphasized efficiency and aesthetic elegance, rather than rapid construction and structural redundancy. But scattered examples survived into the 21st century, preserved as historical monuments to American engineering innovation under combat conditions. The Pont Mitchell across the Seine River near Rouen stands today as sole remaining example of 1944-era American combat bridge construction. French historical preservation societies maintain the span in its original configuration, complete with timber decking and steel I-beam superstructure that offends traditional engineering aesthetics, but demonstrates brutal effectiveness of American wartime methodology. Contemporary engineering analysis of Pont Mitchell reveals construction quality that barely meets modern safety standards while providing load capacity far exceeding calculated minimum requirements. The bridge embodies Mitchell's philosophy of structural redundancy, compensating for construction imprecision. Every component is oversized, every connection reinforced beyond necessity. Every support post extends deeper than calculations indicate essential. German engineering sought elegance through precise calculation. American engineering achieved reliability through overwhelming material application. The difference defined not only bridge construction methodology, but broader strategic approaches to industrial warfare that determined outcome of the European campaign. Germany attempted to win through superior efficiency and optimal resource utilization. America won through industrial capacity that rendered efficiency considerations tactically irrelevant. Weber survived the war and returned to civilian engineering practice in Munich, where he spent 3 decades designing bridges that met German standards for architectural elegance and structural efficiency. He never publicly discussed his wartime observations of American engineering methodology, but colleagues noted his unusual emphasis on construction speed in project planning discussions that typically focused on optimal design and material economy. In 1978, Weber attended an international engineering conference in Washington, where Mitchell presented paper on wartime construction methodology. The two men met briefly after presentation, two old soldiers who'd once opposed each other across French River while pursuing different visions of how bridges should be built. "Your spans offended every principle of proper engineering," Weber admitted through a translator, his English limited despite decades of post-war international professional interaction. But they worked. That's what mattered in 1944. I wrote reports saying American bridges would fail under sustained traffic. They never did. Your methodology was correct for wartime conditions, even though it violated peacetime standards. Mitchell nodded with professional respect that transcended former hostilities. We weren't building monuments. We were building tools to win a war. Different objectives require different methods. Your bridges were beautiful examples of engineering art. Ours were industrial products that happened to cross rivers. Both approaches have merit depending on context and requirements. The conversation lasted 20 minutes. Two engineering officers discussing technical details with professional courtesy that acknowledged different philosophical approaches to solving identical problems. Weber returned to Munich with renewed appreciation for American pragmatism that achieved strategic success through abandoning peacetime standards in favor of wartime effectiveness. Mitchell gained perspective on German engineering excellence that his wartime experience had never allowed him to appreciate fully. The legacy extends beyond military engineering into civilian construction methodology that evolved from wartime innovations. Prefabricated bridge components became standard practice in commercial construction during post-war highway expansion. Standardized structural elements that allowed rapid assembly without custom fabrication transformed how modern infrastructure projects were planned and executed across industrialized nations. The interstate highway system built across America during 1950s and 60s incorporated bridge construction techniques developed by combat engineers in France. Standardized beam lengths, prefabricated deck sections, and assembly procedures that prioritized construction speed over engineering elegance. The methodology that had won war in Europe helped build transportation infrastructure that defined American economic expansion during latter half of 20th century. Contemporary logistics analysis reveals that American bridge building capacity contributed decisively to Allied victory in Europe by eliminating tactical advantage of defensive demolition operations. German forces could no longer trade space for time by destroying crossings and retreating to next river line. American engineers simply replaced destroyed spans faster than Wehrmacht units could establish new defensive positions along subsequent barriers. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.